Welcome to SIIMcast, a podcast brought to you by the Society for Imaging Informatics in Medicine.
Welcome to this episode of SIIMcast. This is yet another in a long line of our My Informatics journey with the one, the only, Dr. DICOM. Steve Horii is a man that really needs no introduction. He is well known for being one of the fathers of DICOM, and for those of you that have seen him at the annual meeting, he always has some very insightful questions when he walks up to the microphone. I hope everyone enjoys this recording as much as we did. And welcome to this episode of SIIMcast. We have Dr. Steve Horii with us to tell us a little bit about his informatics journey and answer maybe a few questions at the end. Steve, why don't you tell us a bit about how you got into informatics, what influenced you, and what other stories that come to mind?
Okay, well, I'll start at the earliest I can recall, and that's when I was a kid, people would ask me what I wanted to be. And the answer was electrical engineer, which would give you some idea where I was headed. You know, in those days, the user question, you want to be a fireman? You want to be a policeman? You want to be like your dad, architect? No, I want to be an electrical engineer. When I got to college, I took a pre-med. At that point, I had decided I really wanted to go into medicine. And I went to Johns Hopkins, and they had an interesting thing. I think they still do it. It's called an area major. So instead of just majoring in biology or chemistry, you could major in natural sciences, and then any natural science course counted towards your degree credits. So yeah, I took the required stuff from medical school, the usual calculus and organic chemistry and stuff. But when I got to a point where Hopkins allows you to take graduate level courses if you have the prerequisites, and there was one on X-ray crystallography, X-ray diffraction studies. And I was always sort of interested in that, because that story of hemoglobin and how they determined its structure. So I took that class, and it was a fascinating class. But one of the things I had to do was the professor who taught it, who came from one of the universities in California, I don't remember which one, but he brought with him his software to do all this reconstruction stuff, and it wouldn't run on the university's computer. And I never took it's not true. I took one class in computer programming, that was it. By the time I got to Hopkins, I was tutoring my friends in how to write code. I was writing Fortran, so it ages me right away. I am an old Fortran hacker. But his stuff was all in Fortran, but it wouldn't run on, we had what's now like an antique IBM 7094 Model 2, which filled up a good-sized room. I mean, like, a basketball court-sized room. 32K words of memory in a box that was about 6 feet tall, 6 feet wide, and 3 feet deep. And it had a thermometer because it had a critical temperature. But I got his code to run on the machine. And, it basically was modifying. They had this thing called job control language. It basically, you needed to set up disk drives and tape drives. So I figured that all out. And I ran his stuff, and I said, yeah, it's working. But I took the course, so I had to learn all this stuff about how X-ray diffraction works, and not much about X-ray physics, but a lot about, how you determine structure from diffraction patterns. And so I had to learn about things like the Fourier transform, which was probably one of the most important things I ever learned. But it got me interested in this whole idea of how do you determine structure of something. And I thought, gee, that's kind of useful in medicine, right? But I stayed interested. I wanted to do X-ray diffraction stuff after that. I tried to find an MD PhD program. Went to NYU, and they didn't have anybody doing protein X-ray diffraction at the time. So I said, well, okay, and I didn't qualify for the PhD part, but I did get into the medical school. And a typical medical school education until I got to, I think it was my third year. And during my clinical, I still had some time, and I was working in the cell biology department. They had a electron microscope stuff there, and one of the faculty was doing 3D reconstruction of ribosomes from tilted electron microscope images. So he would put a specimen in there, go through a series of angles, accumulate the information, and then he would reconstruct 3D from it. Does that sound like something we do, right? We reconstruct from projections, and that's what he was doing. His software wouldn't run on the hospital's computer. So I said, okay, I'll look at your code. And the job control language at this time had gotten a lot more complicated. I mean, it was almost a quarter-inch stack of, in those days, still punch cards to get it to run. And I was having a lot of problems. I finally had to talk to one of the system operators and said, oh, you need to set up that external drive, because his arrays were huge. They were bigger than would fit in the core memory in those days. So you had to scratch right onto it. And she said, that's the problem. You've got to make sure you set up that external disk drive with the right property. So I figured she showed me how to do that. I'd got that done. We ran his code and worked fine. But the chairman of cell biology at that point came to me one day and said, what are you thinking about doing as a residency? And I said, well, I went to this talk on CT scans. It was a new thing in those days. And the physicist explained how it all worked. And I thought, that's a lot of similarity to what I've been doing. The math is the same. And so I thought, well, maybe radiology. Those guys are doing interesting stuff. 2 days later, got a call from the chairman of radiology, it was Norman Chase. And he said, I'd like to speak with you. So I said, fine. I went and talked with him. And he spent most of the time talking about world events. But he also said, what are you interested in doing? I said, well, I'm interested in radiology because I've seen you guys have this CT machine now. It's a new thing. And I understand how it all works. And he said, how about, I understand you're doing a lot of computer stuff. And I said, yeah. And he said, well, we're looking for residents who have an interest in computers and radiology. So he's a pretty forward-thinking guy, right? So I said, yeah, that's exactly my interest. And he said, tell you what, just I was getting ready to leave, he said, if you want a residency next year, you've got it. We got to go through the match, but we'll put you at the top of our list. You'll have that residency slot. And they took me right out of medical school, right? I didn't do an internship year. So I had to do a 4-year, in those days, radiology residencies were 3 years plus a fellowship. But I had to do 4 years because that first year was really my internship year. And then the 4th year was my fellowship year. So I did 4 years, but I did it as a sort of a combined thing. But during that time, the word got out in the department that I was this guy who did computer stuff. And so they said, because I had also, the other thing I did some work in the physiology department. They had an old PDP-8 that wasn't being used much. And they said, we'd like to do a couple of things. We've got some old stuff that runs on that. If you're willing to sort of keep it running for us, you can use it as much as you want. Much time is on a computer as I wanted. It's great stuff. So I was running their computer, and then the folks in radiology, there were 2 people working on, a physicist and nuclear medicine. She was also a PhD, and the other guy was an electrical engineer. And they said, we're working on building a workstation display system, they called it, that could view CT and other images side by side. And they said, we're interested in nuclear medicine right now because we're doing a lot of combined CT and brain scans, and we'd like to be able to display those. So I said, yeah, I'm interested in working on that. So they salvaged a computer left over from the first CT scanner. It was decommissioned, and they took the computer from, it was a mini computer, and they took the tape drive. And then we said, well, you need a display memory. They bought a 1024 by 1024 16-bit display thing, and it cost $20,000. And it was a whole box that fit in the rack. But we built that workstation, and we could show images side by side of a color image from the Nuke Med and the grayscale image from CT. And I think we published, I think it was one of the SPIE meetings, medical imaging meetings. And I got invited to go to that. I didn't give that presentation, but we were also getting interested. The Nuke Med people said, hey, we'd like to be able to look at all images in nuclear medicine, not just have to run over to radiology to put the films up in those days. So we said, well, for the digital stuff, we can probably help out with that. So we started working on this unified workstation for them that they could look at images from multiple. We had to break the encryption codes or storage codes for magnetic tape because all the CT images and everything were stored on mag tape, 9-track mag tape, but the vendors all had their own formats. And we had to sign non-disclosure agreements to look at them. But our guys basically figured out how to do a dump of the tape, and we could see how the data was being stored. And so we were able to read the tapes, look at the images. And so we put together a paper on, I think, a multi-imaging workstation. And that was presented, I think, at the first PAX. And it might have been, there was a meeting in 1981, I think, that preceded the first PAX meeting. It was organized by Sam Dwyer. And the big emphasis on it was digital subtraction angiography was the big thing now. So they wanted, the whole meeting was about digital imaging. And we talked about our workstation. And we sat down with Sam at lunch one day, and he said, he said, I'm thinking this is the kind of thing that should be generalized to all radiology, not just nuclear medicine or not just a particular section. And he said, we're looking at that at University of Kansas. So that next meeting was organized, and I don't remember whether there were two early ones. One was at Newport Beach and the other was at University of Kansas or in Kansas City. And so we went there and we gave our talk about that workstation design and what the thoughts about it were. And other people were starting to talk about, we're interested in doing this. I think there was somebody from, besides Kansas, there was somebody from University of California, LA, and it was Bernie Wang, I believe, and said, we're interested in looking at this idea of, and by that time, Sam Dwyer had called it a picture archiving and communication system, a PACS. And that's sort of where the term originated. And after that, they had a meeting about it every year, and we started presenting our papers, and pretty soon other universities got interested. So it was Duke and UCLA, USC, trying to think of who else, University of Chicago, I think was in on it, University of Arizona. And the early talks were, really basic stuff that we think about now, but it's how do we communicate the things? How do we get the images from the vendors because they're all proprietary? And then how do we display them so radiologists can actually use them? We were thinking more about the hardware and how do you do this? How do you get the images there and display them? But at that meeting, we had someone from the University of Utah and one of our people, who's one of these engineers who had worked on this stuff. They gave a couple of talks on why we need standards for the images, right? They said, this is crazy. The researchers are going nuts because they have to sign non-disclosure to look at the tapes, and then they have to figure out how to read them. Their guys had to write their own code to read the tapes. And they said, this is crazy. And it was not long after that I got a call from Sam Dwyer. And he said, you might be interested in this committee that's being formed. And they're looking at developing a standard for interchanging digital medical images across multiple machines. In those days, it was from a machine to a device. So from a machine to a workstation or a machine to a printer, whatever. It was basically point-to-point idea. So he said, you should let these people know. And he told me who to contact. And it was a couple of people from FDA and Joe Gitlin, right? And they said, well, you should come to the first meeting and we'll find out what our charter is. So I went to that first meeting, and it was the American College of Radiology representing radiologists and NEMA, the National Electrical Manufacturers Association, representing the manufacturers. And they had very strict rules about meetings. Like the manufacturers were not allowed to talk about individual products. They couldn't talk about what their sales had been like. They couldn't suggest a technical solution that favored them. So, like, for example, one of the first things we did was looked at DECRAD as a way of interfacing stuff. The problem is that one of the manufacturers used DECRAD as their communication standard. So it's like, it's proprietary, right?
Yeah.
So they said, no, we can't use that. That's how we came up with this 50-pin point-to-point cable, which was an interesting thing. One of the things we struggled with is the connectors. And we found it because we needed a connector, again, that wouldn't buy us any. Well, we found one that's used on multiple line telephones back in the day. It's a 50-pin connector, a ribbon connector, they called it. Yep. Then we realized, well, we have transmit and receive. So the cable has to cross over some point in it. So the transmit side goes to the receive pins on the other side and vice versa. It was a complicated cable. You could get them made for you, but that became the standard. And so we started in 82 and we had the standard, I guess the first formal work began in 83, but we got the standard published by 85 and 3 years to work on that. And I was on 2 of the working groups. It turns out that's a really good way when you got a big project like this to break it down. And so we had domain experts, like all the electrical engineering people were working in working group 1, which is how do you do the physical interface? What drivers do you need? What, ICs do you need in there? What the signals have to look like. And we used as many standards as we could. So we used an RS something standard. It wasn't 232, it was another standard. The connectors were a standard, so it was easy to, say, hey, this is already a standard. We don't care if it's one vendor that uses it. It's a standard, so anybody can use it. And they worked on that. The other group, I was in working group 2, which looked at the data formats. So they always asked me, what do you guys need when you look at an image to be able to interpret it? We said, we know the patient name and all that stuff, the ID number. But what about the image itself? What do you need to know? Well, we need to be able to know what the pixel values are. right? Because it's the variation in the pixel values that tells us in a CT scan about what what attenuation is. And plain x-rays, although there were no digital plain x-rays at the time, there were people digitizing them, but there were no straight digital x-ray stuff. So we were concentrating on CT and nuclear medicine because they were both digital. So we came up with the digital metadata, the stuff in DICOM. These are the things you need to know. And then as we got more image types on when we would just add more, we called attributes, the things that describe, what is it that describes it? What's your word size for the computer? What's your number of bits per pixel? And how do you encode those bits? When you send them, there were two classes of computers, large endian and small endian, right? And when you're talking about a multi-bit word, you send the high order bit first or the low order bit first. So there was that discussion to work out. And what they did is one of the guys, Dave Clooney, I think, he said, I can write you that code right here in 5 minutes. So he wrote us a little thing and he said, yeah, here's how you switch the bit order. So it doesn't matter which byte comes first. You can flip them around. So he said, okay, then that solves that problem. You give this code away to everybody and don't have to worry about it. But we were meeting at an incredible schedule. We were meeting about 4 days a month, every month. We took a little break during the summer, but basically it's 4 days. And you can imagine to take a radiologist away from working 4 days a month, that's a lot to ask. But Norm Chase said, this is important stuff. He said, I'll make sure you get the time off. I'll talk to your section chairs and say you get the time off and we'll pay for your expenses, all your travel and stuff. The ACR said, we'll pay for your travel expenses. Norm Chase said, no, I'll pay for your travel and stuff. We owe a lot because I wasn't the only radiologist. There was, what was his name, from University of Chicago. He was a radiologist, and then a fellow from University of Wisconsin. I think there were just 3 of us. Although the co-chair, we still had very early on the concept of one of the co-chairs be a radiologist and the other co-chair be from the manufacturers. We always had that structure. And that way you had sort of a balance between the two desires of what you want the standard to be. And we got into that and designed this standard, a 50-pin point-to-point, and published the study. And I think I only know of like 2 implementations of it. General Electric had one, and theirs was a PC that sat next to the CT machine. And one side they used a proprietary version of Ethernet. They called it GE-net or something, but it looked it was the same typical RJ connector that you have. But they did something. It wasn't standard Ethernet because Ethernet hadn't been a standard yet. Yeah. But they took what was out there and they just modified it so nobody else could use it, I think. But the other end was a 50-pin connector. And they showed that it could connect to their control console is what they were doing at the time. It was a quick connection for them. They could demonstrate that it worked. And then a company called... there was Desjardins Research Systems, and it turned out that Wayne Desjardins, who was the president of the company, was a classmate of mine at Hopkins, but I didn't know that because he was in the engineering school. So we didn't have any overlap in classes. But I was reviewing his small business grant thing at the NIH, and I reading through his CV and the grant application said, this guy went to Hopkins and he graduated the same year. But his proposal was good. He was designing a chipset to quickly process the DICOM levels, the stuff it had to do to get. So we funded it, and they came out with the first that I know of, the first board, because the IBM one was a whole PC. This was a single board that did all the interface stuff, and you plugged it into a PC, but the PC just controlled it. And then it had a 50-pin connector on it, and you could send stuff to the PC however you wanted. You could put a floppy disk in there. And if you had a network, you could use it if it was one that the computer supported. And sort of during those days is about the time that Ethernet 802.3 or whatever became a standard. Then word got around that, the point-to-point was a good idea, but, we got computer networks now. So we got to look at that. And that became the start of the switch from the ACR 50-pin to started out as the ACR, NEMA standard for networks. And we became DICOM when we realized there's other medical specialties who want this stuff. There's people in cardiology who wanted digital images. The radiographers, the Fuji digital phosphor plate system came out. And so now you could get digital radiographs. And so we said, okay, we've got to start accommodating more than just CT and MR machines, nuclear medicine, and different countries. It wasn't just the US. We had the Japanese be interested. We had some Chinese applicants. And so now we had to think about things like language. Like, how do you code a patient name in ASCII?
Right.
Well, that's not such a great thing. So we went through all the various ways that different countries digitally coded their languages. And the Chinese was tough because they have so many characters. So how do you code that? Well, they have a way of going to more than one byte. There's a little shift thing, and it tells you this character requires so many bytes to express. So, but we had to accommodate that. So it's all in the standard, as you can accommodate multiple character sets. The default one for the US was ASCII, but there's multiple other ones. And that was part of the fun. And then the naming conventions, right? Different nationalities, they have different way of naming people. And some names get to be extremely long. And so we had to accommodate the length of the name. And then the networking part. We first looked at something called ISO OSI, Open Systems Interconnect, which is a specification that International Standards Organization came out with. It's a 7-layer system, starts up at application layer, goes all the way down to physical layer. So we looked at that, and sort of what made it tough is there's a book of a standard for each level. Right. And we couldn't find anybody that actually implemented the whole thing. The nice thing about it is it gave you a good idea of how to structure a network design, right? So you could say, well, I need the physical layer. No question about that. We can specify that's pretty easy. Use one of the standards. And we look at the data link layer. Well, that sort of makes sense too, because how do you control transmission across the network? And all the way up to probably the section that starts to cover whether you need to encode that some way that's secure. So that's all handled transport layer. And then you go application is just what does the user see kind of stuff. But we looked at only the lower layers, really only what they needed. And we had Ethernet to make the network part that was straightforward. Everybody was implementing it. You could get the drivers from just about anybody. And then the rest of the stuff, we had to expand our library of the elements to describe the wide variety of images that we were getting now. And so we still had people that specific task was to work on that data dictionary and figure out what we needed. We had another group that was looking at what does it have to do with the functionality at the upper levels. There was a whole idea of you need to send an acknowledgement, when you're going to get a message over, how do you do that? How do you handle the handshakes? So we did all that sort of stuff, and that was what we came up with. We wound up not using all of ISO OSI because it was just way too cumbersome. Then we had a guy come from AT&T, because we were now starting to look at what happens if we want to talk to a hospital information system, not just imaging. Now you got a PACS. What do you want to do if you want to talk to a RIS or a HIS or what? So we had a guy from Bell Labs who came in and said, well, one of the things you want to look at is what's your data structure like? Do you have a data model? And we said, well, we kind of break it down into a patient and has an images in the exam. And they said, no, well, there's a structure to that, right? You have a patient, you have an exam, you have a series, you have, images. So we started developing this idea of an information model. And he said, well, a good way to do this, not necessarily to encode it, but a good way to do it is to look at object-oriented design. So now all of a sudden, all of us we went and got the books on designing object-oriented systems. And we had to learn all that stuff, what entities meant and what attributes meant and how they talk to each other. And it became a very logical way of building an information model. And that's what we did. That all was a result of the guy from AT&T and then a bunch of us who said, yeah, when you start to look at this, it makes perfect sense. So if you look at the DICOM information models, they're all based on an object-oriented design. And it made things a lot easier. It made interfacing with other systems a lot easier because look at what their information model looks like. Where are the attributes cross over? What can we use? HL7. This was before FHIR, so it was HL7. We could do that. We understand HL7. It's also a message-based system, although they have like limited field lengths and stuff. And DICOM, a lot of the fields are variable length. But that was easy enough to accommodate. Tell us how long your field is. We'll just fit it in there. And that also kicked off the IAG, Integrating Healthcare Enterprise effort, which was started by another group. But their idea was to take, again, existing standard. Don't invent new stuff. So you got DICOM, you got HL7, and that's where it took off. And they started developing as well. Not only what do the images look like, but how do you get them? What are these, how would you describe what happens in a radiology department? So they were looking at sort of the workflow stuff. And that's where those profiles come from. If you look at the profiles, they're just basically describing what you do to get to the image. Once you get to the image, then DICOM can handle that. But as getting to the image, you need to exchange those HL7 messages in between terminals and the system hardware. And when you're communicating with DICOM, it's okay. You need an interface of the two to talk to each other, so I get the patient information across. But that's kind of what, those profiles in the IHE, that's where they came from, was a group that looked at the information models. So again, that turned out to be a useful thing. And then a workflow model. So how do we go? We have actors and we have those who carry out the actions. And so how do we connect these things together? That's basically what they did. And it's still going on, of course, so DICOM is still evolving. So, we had the web-based access, and it was clearly something we needed to do. And then the various tools you can use to build those. And of course, now the thing is, what are we doing about AI applications? How are you going to get those to talk within a radiology system? What are they going to do? How do you describe what's doing? When do you pick up the data? How do you get access to an imaging set? That's pretty straightforward. If your training sets in DICOM and your test sets in DICOM, it's straightforward. But the questions are, well, now you got to anonymize some of the stuff. And that turns out to be you can get applications now that'll go in and take out all the 18 or 16 things that they say shouldn't be in there if you want to de-identify something. So that's the progress. I mean, all while I'm doing clinical radiology, now, the DICOM committee wasn't meeting 4 days every month now for a year. It was meeting, we would meet a few times a year, and then we had a lot of telephone conversations, and we get minutes sent out. And then the standard was still available for free. Anyone wants it. And we do routine updates. Typically, we issue a new edition every year because all the changes and updates that get made. Corrections, like we found out that we had designed in a way to hack into the system. Back in the days of ultrasound, there were more than one company. A lot of manufacturers had switched to, when we got rid of film, they had switched to these 3.5-inch magneto-optical discs. They look like a fat floppy disk cartridge. But yeah, well, like mini discs. But most of them were magneto-optical, so you could actually rewrite them. But what the manufacturers are using it for was you'd put a disk in the machine, it would record all your images on it, then you could take it to a printer, and the laser printer would read it, and it would print your images, because we were still reading ultrasound from film mostly. That was one thing they could do. But we said, one of the problems is there's different formats on those disks, right? The images can be DICOM, but they also be TIFF, because some of the vendors put their stuff out in TIFF. And so we said, okay, so we built a little preamble in there. And we said, if you see the word DCM in there, it's a DICOM format. If you see TIFF, it's a TIFF format. But there's space in there that was reserved. Well, it turns out that someone figured out I could put code in that space. And I could basically hack the DICOM. Whatever's receiving the data could be hacked by putting executable code in there. And it came out in a paper, and we, that's why there was that article that came out that says DICOM has been hacked. What do we do now? Kind of stuff. Yeah. And it was a little overblown, but that was, that we discovered that. We said, okay, we got to figure out how to prevent that. But it was done to make it easier for people to use. You got a little disk, you can use it for multiple image formats. It doesn't have to be DICOM. It can be TIFF. It can be something else. So it was good intent, but we did it in a way that made it too easy to inject the executable code in there. The security people worked on it. I'm not entirely sure what their cure was. I think it might be you've got to take a look at what's in there first. You can't just blindly read it. You have to put that in a temporary storage somewhere and make sure it's not code. It's like that hacks that people do with SQL, where you put code into a SQL thing. Yeah, and executes it and it can screw things up. So it's the same sort of ideas. That's what we enabled. Unintentionally enabled, but they've got a fix for it. So, but that's the kind of thing that keeps DICOM folks busy. That and then new imaging techniques all the time. So yeah, I was keeping up, and I still would go to the DICOM meetings, and they were always sort of interesting. The one in Japan was the one you probably saw the slides about. This was in a karaoke bar. Well, what they had done is the Japanese came up with a format called ISAC, Image Save and Carry. and they wanted to use DICOM, which was fine. But they have a restriction in Japan about media. The media has to be encrypted. And they said, okay, the problem is that their encryption method was proprietary. And they said it doesn't have to be encrypted for other countries, but, we sell the drives worldwide for this. And they said, we currently have two versions. We have a Japan market version that has the encryption stuff in it, and a rest of the world version that doesn't, unless someone wants the encryption stuff. But we said, well, the problem with the DICOMs is we don't really have a way to do that. What we wound up doing is took days of compromising on this and discussing, well, what can we do to make sure that you can do it, the Japanese can do what they want, we can still use DICOM. The images on it can still be in DICOM, but they're encrypted. But the images that we make are not encrypted. Some people can choose to do that, but that's not part of the standard. So we came up with, okay, there'll be the standard for the U.S. to use that 5.25" magneto-optical media for storing and transmitting data. The Japanese can use ISAC. But that way it preserved their other use of DICOM because the other imaging that they did was all DICOM stuff. Hitachi and Fuji they made DICOM conformant stuff. And they said ISAC can talk to those systems if you use their drive, the ISAC compatible. There were several manufacturers, ISAC compatible drive. It would decode it so the device got DICOM. But that was the solution we came up with, was compromise. There'll be two versions of this disk. There's the ISAC version and there's the DICOM version. One other thing is, it's just 2 days of meetings, and this little conference was smaller than this, and all the Japanese guys were smoking. So I said, I think we got like a lifetime worth of, secondhand smoke from those meetings. But we went to this little karaoke bar. I mean, it was sort of fun, because they had ringers in there, right? They had these Japanese women who were good singers. And it turns out, we had some folks in the DICOM community who were pretty good singers. Yeah, it was fun. But yeah, there was enough alcohol going around to kind of make everybody relax. I think that a lot of Japanese are like me, and other Asians as well, as we don't have a great tolerance for alcohol,
Right.
because we have a low alcohol dehydrogenase level. So actually, my internal medicine guy said, you probably should avoid alcohol. It could damage your liver more easily than it does other people. So I said, okay, I just don't drink much. Taste the wine if my wife's having some, but.
So while you take your sip, I actually have a question that I realized in my entire career, it never occurred to me to ask. Everyone knows that DICOM is a desk standard, but if you look carefully, DICOM 3 is the standard that we use right now. What was DICOM 1?
The 3 was kind of a funny misnomer. The DICOM standard has always been identified by the year. So it would be DICOM, 1993 or something like that, and DICOM. But the DICOM 3 came about because it was the third version we were working on. It's not the formal description of it. It's got a standard number, like NEMA has a standard number, and it's got the year in it is what it is. What the discussion is now, this is sort of going on behind the scenes of all this stuff, is that there is some interest in actually spinning off DICOM to a different organization besides NEMA. NEMA has a group, that's called MEDA, that does the medical imaging stuff. And NEMA's run it for years because, the meetings are easy to organize, that we have the right legal review of all the minutes to make sure there's no breaches of the conflict of interest stuff. And we think that NEMA may actually hold the copyright to DICOM. They do have, the DICOM name is actually a service mark. And so that belongs to NEMA. So a lot of questions about how we would do this if we really want to do it. And we're not entirely sure whether, there's people who are pro and there's people who are con. And so the tough part is how we're going to do it if it happens. But yeah, there is another organization that wants to do it instead of NEMA. NEMA doesn't want to give it up. So, and all the manufacturers are members of NEMA.
Right.
They would have to be another member of another organization. The way NEMA works, the way they get funded is it's based on the manufacturer's sales. So their dues to NEMA are based on their yearly sales.
Percentage.
Yeah, they pay a percentage of that as their NEMA dues. And then actually, if you're a physician member, a medical member, there's also, there's dues, but it's much lower than what the manufacturers are paying. It's a small amount. I don't know whether I think we asked SIIM to be a member, if I'm not mistaken. I got to check on that, whether that's true, but I know we did. Things like the ACR is a member. In fact, from the very beginning, you had to be an ACR member to be on the DICOM Standards Committee. They changed that. We got gastroenterologists and we got cardiologists. And so then we changed. But that was the other interesting thing, was working with the other specialists. Because like we found out right away, digital pathology is a challenge.
Yeah.
Because we have a certain specification in DICOM of how big the number of rows and number of columns of a matrix can be.
Yeah.
Right? And the problem is the digital pathology images exceed that limit.
Yeah.
So that was a real problem. What saved us was the idea of it's one that's used by one of the compression algorithms where they basically break it up into smaller pieces. They tile it. It's a compression model, pyramid compression model, right? I think that's what Stentor used to use. They would send you the low resolution image right away. And as you sat there, it would get better and better. And that was, they were sending the different tiles. And that's kind of what we worked out with pathology and the way to describe that in coding so that you could send their images. Good. Actually, we had talked to NASA. If you think their images are big, you should see some of the NASA ones because they have the satellite and it'll capture like a very long image. And they told us the size of it and we were just amazed. And we also talked to some people from, well, they were the NSA people. They were fascinated by, they came to us and said, how are you guys storing all this stuff? And, because they wouldn't entirely tell us what they were doing. But this was when I was at Georgetown. We took them through, we have they had two optical disc jukebox. These are 12-inch optical disc. And they took a look at it and they said, yeah, that kind of looks familiar, which gave us a lot of information right away. But yeah, they said, no, we certainly can't tell you the formats or anything. That stuff's all encrypted anyway. But yeah, and I purposely I loaded an image taken from one of our declassified spy satellites, but it was a picture of the Pentagon.
Right.
And I made sure that I could pull that image up as to show what the images look like. They didn't seem to mind it at all. I just popped the thing up because it was a declassified image. Right. I think there was that one image that got published that was supposed to be classified. Yeah, it got published in one of the journals in Aviation Week or something. It was a spy satellite photo taken of a Russian shipbuilding facility. And right away, that told you what the resolution of the satellite was. And that's the kind of stuff they didn't want to give away. Yeah. Although there were hints. A friend of mine worked at TRW and he went in and went on a tour and he asked them, he said, what's the size of the telescope mirror? He said, I can't tell you that, but just imagine this. Suppose we took the Hubble telescope and pointed at Earth. That's all he had to say. Yep. My friend said, okay, I know how big the mirror is. It's been published since, but that's, at the time you just gave away the size of your mirror. He had clearance for class. I mean, he wouldn't have been allowed to walk around that part of TRW if he didn't.
SIIMcast has been brought to you by the Society of Imaging Informatics in Medicine. Please visit our website at SIIM.org for more information and educational content, including webinars and an archive of prior episodes. Please follow us on Twitter at SIIM_tweets. Thank you to our listeners for your continued support.